Hello there, and welcome to the Sleepy Space Channel. Tonight, we'll be drifting slowly outward into the soft sea between our galaxy and the next. The space between the Milky Way and Andromeda is not empty. It is layered with the patient outer atmosphere of our galaxy, threaded with an ancient light that has been with the universe since long before any star, and quietly bridged by a faint scaffolding of unseen gravity. We'll move gently past the soft halo of home into the warm, hot drift of intergalactic gas, beneath the slow glow of the cosmic background, and inward at last toward the far shore of Andromeda. There is no hurry. The journey takes light itself 2.5 million years. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy. Let's begin. The journey between our galaxy and the next does not begin with a leap into emptiness. It begins with a slow softening of the place we already live in. The Milky Way does not end at any sharp boundary, and the space outside it is not the cold vacuum of imagination. The galaxy fades by gradient, and the gradient itself is full of quiet detail. To begin moving toward Andromeda, you would first move outward through the part of the galaxy you cannot see, through gas you cannot feel, through stars too old to crowd, through gravity that grows softer at every step but never quite lets go. The first region you would pass through is one you already live inside. The Sun sits inside a vast soft cavity in the interstellar medium, a region where the gas between the stars is thinner than almost anywhere else in the galaxy's disk. This region is sometimes called the local bubble, and it is about 300 light-years across at its widest. You can think of it as a long faded weather system in the interstellar gas. A chain of massive stars exploded as supernovae over the past 10 or 20 million years, and each explosion swept up the surrounding gas, pushed it outward, heated what remained, and left behind a bubble of very thin, very hot plasma. The Sun has been drifting through this bubble for the past few million years, and it will continue to drift through it for a few million more before crossing into denser interstellar gas again. Inside the bubble, the gas is hot in the strict thermodynamic sense, but you would not feel any warmth from it. The temperature inside the bubble is around 1,000,000 Kelvin, but there is so little material per unit volume that there is essentially no heat content. There is roughly 1 hydrogen atom for every 10 cubic centimeters of space inside this region. To call it a vacuum by laboratory standards would be generous. It is mostly nothing, and yet it is also the medium your local night sky is suspended in. The starlight you see is filtered through it. The cosmic rays that wander through Earth's upper atmosphere have traveled through it. The solar wind, blown outward from the Sun, slows down when it meets it, and that slowing is what defines the outer boundary of the solar system. So you have already lived inside the first region of the journey for your entire life. The walls of the bubble are denser than the interior, cooler, and contain younger stars. If you moved outward in almost any direction from where the Sun currently drifts, you would eventually pass through one of these wall regions and into the wider interstellar medium of the galactic disk. The gas there is more varied. In some places it is cold and dense, with hydrogen pulled together into molecules and dust grains scattered through it. These are the great star nurseries, the regions where new stars are still being born. In other places, the gas is warmer and more diffuse, with hydrogen atoms moving freely and slowly. In still others, the gas is warmer still and partly ionized, so that the hydrogen atoms have given up some of their electrons. The interstellar medium is not one thing. It is at least four things at once, layered across a galaxy that is mostly made of empty space anyway. As you continued outward from the bubble's wall, you would move through these layers in turn. You would pass through cold molecular clouds and the warm neutral gas around them. You would drift through diffuse ionized clouds that glow faintly when astronomers look for them with the right kind of telescope. You would pass between stars whose density falls off slowly the further out you go. There would be many fewer dust grains than there were near the disk's midplane, because the dust is concentrated along the disk's central plane. You would still see stars all around you, and the galaxy's spiral arms would look the way they always do, quietly turning, slowly drifting, holding the same patient shape they have held for billions of years. The galaxy's disk is roughly 100,000 light-years across. The Sun sits about 26,000 light-years from the center, and so the journey to the outer edge of the stellar disk in the direction of Andromeda is something on the order of 70,000 light-years just to get out of the stellar disk itself. That is already a great distance. At the speed of any spacecraft humans have ever built, the crossing of that first leg alone would take far longer than the entire age of the human species so far. And yet, on the scale of the full crossing to Andromeda, this first leg is only the beginning. As you reached the outer disk, the stars would thin out gradually. There would be no single edge, only a soft falling off of density. The cold molecular clouds would disappear long before the stars do, because new stars only form in regions where gas can cool and gather. The very outermost stars would be sparse and old, and beyond them, you would still find a faint cloud of gas extending past the stellar disk, called the gaseous extended disk. The hydrogen there is mostly neutral, mostly quiet, and slowly warped by the gravitational tug of distant satellites. It marks the place where the stellar disk has clearly ended, but the galaxy itself has not. And then you would enter the stellar halo. This is the region above and below the disk's plane, and out beyond the disk's edge, where the galaxy keeps its oldest residence. The halo is sparsely populated. There are no spiral arms here, no nurseries, no recent star formation. The stars in the halo are old, many of them as old as the universe itself, and they orbit the galaxy on long, looping paths that take them high above and far below the disk. They drift through the halo on orbits that have not changed in billions of years. They were here before the Sun was born. They will be here long after the Sun has finished its life and become a white dwarf, and even longer after that, still drifting on the same patient orbits. Threaded through the halo are dense balls of stars called globular clusters. The Milky Way has about 150 of them. Each one is a small, compact swarm of hundreds of thousands of old stars, bound together by their mutual gravity. They have orbited the galaxy for as long as the galaxy has existed, and they will continue to orbit it for as long as the galaxy continues to exist. From inside one of these clusters, the night sky would be drenched in stars, bright stars in every direction, with no need for any moon or sun to light the night. From outside the cluster, looking inward, the cluster would appear as a small, luminous ball of light, like a far-off lantern in the dark. As you moved outward through the halo, you would pass several of these clusters. They would be the most concentrated points of light in an otherwise sparse region. The halo also contains long, thin ribbons of stars that wind through it on slow trajectories. These are called stellar streams, and they are the remains of small galaxies that were torn apart by the Milky Way's gravity in the distant past. When a small galaxy comes too close to a larger one, the larger galaxy's gravity stretches it out, and the smaller galaxy's stars are eventually spread along a long arc that traces out the path of the original orbit. Each stream is the soft afterimage of a galaxy that no longer exists. The Milky Way's halo is threaded with several of these, and you would drift through one or two of them on the way out. The most prominent is called the Sagittarius stream, named for the small galaxy that was its source. From inside one of these streams, you would not even know you were in one. The stars would be too spread out to seem like a structure. But from outside, looking down on the halo, you would see them as gentle arcs traced across the sky, like the wake of long-vanished ships. The stellar halo of the Milky Way extends much further than the stellar disk. Stars belonging to the halo have been found at distances of 300,000 and 400,000 light-years from the galaxy's center. In the direction of Andromeda, the halo blends gradually into the in-between space, not because there is an edge, but because the stars become so sparse that you would have to wait a long time before encountering another one. And here, you would begin to notice something quiet and deep about the journey you are taking. The galaxy you came from has no clean edge. It has only a slow fading. The center is bright, the disk is bright, the halo is dim, and beyond the halo, the brightness simply fades until it is no longer distinguishable from the rest of the universe. The Milky Way's last contribution to the journey is not a final star, or a final cloud, or a final cluster. It is a gentle thinning of presence. You move outward, and the galaxy gives less and less of itself to the sky, until at last what surrounds you is something else. That something else is the next region of the crossing, and it is a region most people have never thought about. The galaxy is wrapped in atmospheres no one can see. There is gas beyond the halo of stars, and that gas extends much, much further than the stellar halo itself. To leave the galaxy, in any meaningful sense, you must first leave its atmosphere. And the atmosphere of a galaxy is far larger than the part of the galaxy that glows. That atmosphere is where the journey continues. The stellar halo grows quiet behind you. The disk is now a soft, glowing wheel, seen edge-on from far above. The constellations have lost their familiar shapes long ago. The sun has become a point so dim that if you knew exactly where to look, you might still find it in the swirl of stars below, but you would not be able to pick it out without help. The galaxy you grew up inside has become a piece of scenery rather than a place, and the long crossing has only just begun. Most people, when they imagine the edge of a galaxy, imagine a fairly clean boundary between the stars on one side and empty space on the other. That picture is not quite right. A galaxy is not only a disk of stars and a halo of old wanderers and a hidden gravitational shell of dark matter. It is also a vast, mostly invisible cocoon of hot, thin gas, and that cocoon reaches out far beyond the part of the galaxy that glows. Astronomers call it the circumgalactic medium, or sometimes simply the galactic halo gas. You can think of it as the galaxy's atmosphere, and like Earth's atmosphere, it thins gradually, rather than ending at any clean altitude. It is the place where the galaxy stops being a galaxy and starts being something else, and the transition is slow. The Milky Way's atmosphere of gas extends at least 600,000 light-years out from the galactic center. That is more than 6 times the diameter of the stellar disk. It is a vast, sparse, very hot shell of plasma, mostly ionized hydrogen and helium, with traces of heavier elements that were processed by stars in the disk and then expelled outward. The temperature of this gas is somewhere between 100,000 and a few million Kelvin. The density is very low, but the volume is so enormous that the total mass of this atmosphere is comparable to or larger than the mass of all the visible stars in the galaxy. In other words, when you add up everything you can see in the Milky Way, every star, every nebula, every cloud of gas in the disk, and put it on one side of a scale, and then put the invisible atmosphere of the galaxy on the other side, the atmosphere weighs at least as much. This is one of those facts that, when you encounter it for the first time, gently rearranges your sense of what a galaxy is. Most of the matter in the galaxy is not the part you can see. It is the part you cannot. And not because it is exotic, or hidden, or unusual, but because it is so spread out that no telescope picks it up directly. It is only detectable through absorption, by watching the light of distant quasars on the far side of the galaxy as that light passes through the atmosphere on its way to us. The atmosphere imprints faint, narrow absorption lines on the quasar's spectrum, and from those lines, astronomers reconstruct its temperature, its density, its motion, and its composition. You can imagine the slow detective work involved. The light of a quasar billions of light years away travels for billions of years, finally crossing the soft outer atmosphere of the Milky Way before it reaches a telescope on Earth. Along the way, every small cloud of ionized gas the light has passed through has subtracted a thin slice of its spectrum, leaving a fingerprint. By reading those fingerprints, the soft atmosphere becomes legible. The galaxy's invisible weather becomes visible not in any one image, but in the patient accumulation of thousands of quasar sightlines, each one threading the atmosphere at a slightly different angle. Patience is the instrument here. The atmosphere does not need to glow. It only needs someone willing to look at distant light for long enough. The atmosphere is not a uniform shell. It has structure. There are denser inner regions, closer to the galaxy, and thinner outer regions further out. The temperature varies. The motion of the gas is complex. Some of it falls inward, drawn by gravity, on its way to feed new star formation. Some of it flows outward, pushed by supernovae and stellar winds, on its way to becoming intergalactic gas. There is a continuous cycle between the disk of the galaxy and its atmosphere. Astronomers sometimes call this the galactic fountain. Gas rises from the disk, cools in the upper atmosphere, and falls back down again, sometimes after millions of years of slow travel. The disk and the atmosphere are not separate systems. They are one system, breathing slowly across geological time. When supernovae explode in the disk, they push hot gas upward, sometimes carrying it many thousands of light years above the disk's plane before it slows and begins to cool. The cooling gas eventually rains back down on the disk as cooler clouds, and those clouds may form the next generation of stars. The heavy elements that the supernovae created are mixed into the atmosphere along the way, and from there they make their slow way back into the disk, enriching it for each new round of star formation. The atmosphere is thus also a slow chemical mixer. It is where the galaxy stores its own future, in a sense, and waits. When you continued outward past the edge of the stellar halo and into the deep atmosphere, you would notice the gas around you growing steadily thinner. There would be far fewer ions per cubic meter than there were in the disk. The temperature would still be hot in the technical sense, but you would not feel it. There would be no light reaching you from the gas itself. The atmosphere does not glow invisible light at all. You would only know it was around you because, if you looked at distant quasars, you would see their spectra slightly altered as you crossed each new layer of the atmosphere. The atmosphere would announce itself only through absorption, only through what was missing from the light passing through. Threaded through the atmosphere is the galaxy's magnetic field. The field is faint, much fainter than the magnetic fields of stars or planets, but it is present, and it threads through the atmosphere in long, looping structures. Charged particles, cosmic rays, follow these field lines through the atmosphere, spiraling along their length. Some of these particles came from supernovae in the disk. Others came from sources outside the galaxy entirely. The atmosphere is therefore not just gas. It is also a medium for slow particle traffic, a place where the galaxy and the wider universe exchange messengers continuously. Out beyond the densest part of the atmosphere, the gas becomes so thin that it begins to merge with the gas of the intergalactic medium itself. There is no clean edge here either. The atmosphere of the galaxy thins out into the intergalactic medium with no clear seam. The temperature and density blur together. The transition zone is hundreds of thousands of light years thick. You could not point to a single layer and say, here the Milky Way ends, here the intergalactic begins. The galaxy is connected to its environment, and its environment is connected to the next galaxy, and the next, and the next, across the long quiet of the cosmos. Most of the Milky Way's atmosphere is invisible not only because it is too thin to glow, but also because it is too hot to absorb visible light strongly. It is best detected in the ultraviolet and in X-rays. When astronomers point ultraviolet telescopes at distant quasars, they see a faint but unmistakable signature of the atmosphere written into the quasar's light, the characteristic absorption lines of ionized oxygen, ionized magnesium, ionized silicon, ionized iron. Each absorption line is a tiny fingerprint of the atmosphere along that particular line of sight. By collecting these fingerprints from many lines of sight, astronomers reconstruct the structure of the atmosphere, the way you might reconstruct the shape of a room from the echoes of 1,000 whispered words. The size of the atmosphere matters in another way too. Because the atmosphere extends so far, it overlaps with the atmosphere of any other large galaxy nearby. The Milky Way and Andromeda are about 2.5 million light-years apart, center to center. The atmospheres of the two galaxies are each about 1 million light-years across. Add up the distances, and you find that the two atmospheres very nearly touch each other in the middle of the gap between the galaxies. The soft outer reaches of the Milky Way's atmosphere may already be in contact with the soft outer reaches of Andromeda's. There is gas in the space between the two galaxies that is no longer clearly part of either one. It is shared territory. This is one of the most quietly remarkable facts about the local group. The two great spirals of our family are not separated by clean vacuum. They are separated by their own combined atmospheres, faint and overlapping, threading together at their outer edges. The space between them is not the empty space of the imagination. It is a gentle shared medium, a soft handshake of gas across the long distance, a slow, continuous gradient of density and temperature, with no sharp boundary anywhere. And yet most of this medium is so thin that it would not register on any instrument designed for human comfort. If you stood somewhere in the middle of the gap between the galaxies and held your hand out, you would pass through perhaps a few hundred protons in an entire second. There would be no air to breathe, no warmth to feel, no light to see by, except the dim glow of the cosmic microwave background and the faint scattered light of distant galaxies. And yet you would be standing inside something inside the slow, shared atmosphere of two great spirals, inside the soft reach of the local group, inside a place built out of patience and distance. The atmosphere of the Milky Way is also where the galaxy keeps a kind of memory. Heavy elements that were forged in stellar interiors over billions of years are now suspended in the atmosphere, slowly circulating, waiting their turn to fall back into the disk and become part of the next generation. The atmosphere is the storage room of cosmic chemistry. Every atom of oxygen in your body, every atom of carbon, every atom of iron, was once part of a star that exploded. And after the explosion, some of those atoms may have spent hundreds of millions of years in the galaxy's atmosphere before falling back down to seed the cloud from which the sun would eventually form. Your atoms have lived in the atmosphere before they lived in you. They came from out there, and they are still going. Behind you now, the disk is small. The galaxy's spiral arms are a thin pinwheel, barely larger than your hand at arm's length. The halo of old stars and globular clusters is mostly behind you. The atmosphere of the Milky Way still surrounds you, but more thinly with every passing distance. And ahead, far ahead, but at last beginning to become noticeable, there is the larger story of the in-between, the structure that the universe has built between galaxies, the patient scaffolding of dark matter, and the great soft sea of intergalactic gas. It is time to move past the atmosphere. Beyond the atmosphere of stars and gas, there is another layer of the galaxy, and it is the largest layer of all. It is also, in a quiet way, the most important. Without it, the galaxy you live in would not exist in its current form. The disk would not have stayed together. The halo would not have orbits. The atmosphere would have drifted away long ago. The shape of the entire system is held in place by something you cannot see, and that something extends far beyond every other part of the galaxy. It is called the dark matter halo, and it is the true outer boundary of the Milky Way, if there is one. The dark matter halo is invisible. It does not emit light. It does not absorb light. It does not scatter light. It does not seem to interact with ordinary matter through any of the familiar forces except gravity. And gravity is enough. Through gravity alone, the dark matter halo holds the entire visible galaxy in place. The stars in the disk orbit the center faster than they should, if only the visible matter were there to pull them. The outer stars of the halo move on long looping paths that require more gravity than the visible matter can supply. The atmosphere of the galaxy is contained, not blown away by its own thermal pressure, because something far greater is holding it down. That something is the halo of dark matter that surrounds it all. The mass of the dark matter halo is somewhere around 10 times the mass of all the stars, gas, dust, and other ordinary matter combined. The shape is roughly spherical, with subtle distortions that come from the disk's gravity pulling it slightly inward at the equator. The radius of the halo is roughly 1 million light-years, possibly more. That number is worth saying twice. The visible galaxy is about 100,000 light-years across. The dark matter halo extends 10 times further. The galaxy you can see is a small bright island in the middle of a much larger, invisible structure. What is dark matter made of? That is one of the open questions of physics, and it has been an open question for nearly 100 years. There are several leading possibilities. It could be a particle that interacts only weakly with ordinary matter, sometimes called a weakly interacting massive particle. It could be an extremely light particle called an axion. It could be some entirely new kind of physics that has not yet been imagined. What is clear is that dark matter is something with mass, something that exerts gravity, something that fills the space around galaxies and inside galaxies and between galaxies. It is not nothing. It is just not anything that the eye, or any current telescope, has yet learned to see directly. For our journey, what matters is that the dark matter halo extends out to roughly the halfway point between the Milky Way and Andromeda. Andromeda has its own dark matter halo of comparable size and mass. The two halos almost certainly already overlap at their outer edges. There is no clean point in the gap between the galaxies where the Milky Way's gravity has ended and Andromeda's has begun. The two galaxies are gravitationally tangled together long before you would ever reach Andromeda itself. The transition between one galaxy's gravitational territory and the others is gradual, and somewhere out in the middle, you would pass through a place where the pull of one galaxy and the pull of the other are very nearly balanced. You could call it the gravitational midpoint, or the barycentric region, or the in-between. From that place, both galaxies would feel equally near and equally far, and neither one would be the one you were leaving or the one you were approaching. You would simply be in the middle of a much larger shared structure. In the dark matter halo, you would not feel anything different. Your sense of motion would not change. Your sense of direction would not change. The stars around you, the few that there are, would not look any different. The dark matter does not glow, does not block light, does not interact with you in any way you could notice. And yet it is there. It would be all around you, in every cubic meter, holding the shape of the galaxy you came from and the galaxy you are moving toward. It would also stretch out into the space between, threading the gap as a long, soft bridge of gravity that does not show up on any visible map. This bridge is one of the quiet surprises of the local group. The two largest galaxies are gravitationally linked not only through their mutual attraction across the gap, but through the dark matter that connects them as a continuous structure. Computer simulations of galaxy pairs, like the Milky Way and Andromeda, routinely show that the dark matter does not stop at the visible edge of one galaxy and resume at the visible edge of the other. It forms a continuous filament between the two, dense at each end where the galaxies sit, and thinner but still present in the middle. The two galaxies are joined by an invisible thread, and the thread is part of a much larger cosmic web that connects all the galaxies in the universe to one another, in a sense. There may even be small dwarf galaxies, globular clusters, and isolated stars that drift through this dark matter bridge, far from any host galaxy. They would be very faint, very sparse, very hard to detect, but they would be there, populating the in-between with a thin scattering of light. A few intergalactic globular clusters have been suggested, and a handful of intergalactic stars have been observed in the gaps between galaxies in other systems. The numbers are small. Per unit volume, intergalactic stars are vanishingly rare. But across the entire universe, they may number in the tens of billions because the volume is so enormous. The space between galaxies is mostly empty of stars, but it is not entirely empty. The dark matter halo's outer edge is fuzzy in another way too. There is no clean boundary where the Milky Way's halo ends and intergalactic space begins, because the dark matter density does not fall to zero. It falls off gradually, like the density of an atmosphere, until eventually it becomes indistinguishable from the average density of the wider cosmos. The halo blends into the cosmic web. The cosmic web blends into the deep universe. There are no walls anywhere. The whole structure is one continuous fabric, with denser places where galaxies live and thinner places between them, and an enormous gradient of density from one end to the other. In a sense, the dark matter halo is the part of the galaxy that has always made the galaxy possible. Without it, the galaxy's gas would have been blown apart by the very first generation of supernovae. The stars in the disk would have flown off into intergalactic space long ago, because their orbital speeds are too high for the visible mass to hold them in. The galaxy you live in is the shape of a gravitational well that is mostly invisible. The bright disk is just the small visible center of a much larger basin. You are inside the basin. The basin is wide, and the basin extends almost to the next galaxy. To leave the Milky Way completely, you would have to drift outward until you crossed the very faint outer edge of this halo, where the galaxy's gravity finally becomes too weak to hold you back. That edge is not a sharp one. It is a slow falling off of acceleration. As you drift outward, the galaxy's pull becomes gentler and gentler, until at last there is essentially no acceleration toward home at all. From that point onward, you would move freely through intergalactic space, though even then, the local cosmic web would still influence your motion in subtle ways, and the gravity of Andromeda ahead of you would already be beginning to take over. The Milky Way's outer edge, then, in any meaningful gravitational sense, is somewhere around 1,000,000 light-years from the galactic center. That is roughly halfway to Andromeda. The galaxy reaches almost halfway across the gap, invisibly. So does Andromeda from its side. In the middle, the two galaxies share their gravitational reach, and the space between them is not the space between two isolated islands. It is the space inside a single elongated structure that has two bright concentrations at its two ends. This is one of the gentler perspectives on the journey to Andromeda. You are not crossing an empty void to reach a distant island. You are walking outward through one galaxy's outer atmosphere and gravitational halo into the shared territory of two galaxies that are already touching at their outermost edges, and from there inward through the outer atmosphere and gravitational halo of the other. You are crossing a single soft structure that has two great spirals embedded in it. The journey is long, but it is contained. The dark matter halo of the Milky Way and the dark matter halo of Andromeda are part of the same gentle architecture. You are never truly alone. And yet, there is also a place in the middle of the crossing where the soft architecture of the two galaxies gives way to something even larger, the true intergalactic medium, the thinnest layer of all, the place that fills almost the entire volume of the universe and is, in a strange way, the most populous of all the regions of cosmic space. It is to that medium that the journey must now turn. We come now to the heart of the journey, the truly intergalactic part of the crossing. The medium between the galaxies in the strictest sense, the thin sea of plasma that fills the universe outside of galaxies. Most people, when they think of intergalactic space, imagine pure vacuum. That picture is almost right, but it is gently incomplete. The space between galaxies is the largest reservoir of ordinary matter in the universe, and it is the most overlooked. To understand the intergalactic medium, you can start with two numbers. The first is how much of it there is. By total mass, the intergalactic medium holds roughly half of all the ordinary matter in the universe. Not half of the dark matter that is a different and even larger reservoir. Just half of the ordinary atomic matter. Every atom that ever was, in some sense, has either spent some time in intergalactic space, or is currently in it, or will be. The second number is how thin it is. The average density of the intergalactic medium is roughly 1 hydrogen atom per cubic meter. That is so thin it would seem like perfect vacuum by any standard you might apply on Earth. A cubic meter of air on Earth contains around 10 to the 25th power molecules. A cubic meter of intergalactic space contains around 1. The intergalactic medium is, by terrestrial standards, almost completely nothing. And yet, because it fills the universe, it adds up to more than all the stars in all the galaxies combined. What is it made of? The intergalactic medium is mostly hydrogen, with a smaller fraction of helium and a very small trace of heavier elements. About 3/4 of its mass is hydrogen. About 1/4 is helium. The remaining fraction of a percent is the heavy elements carbon, nitrogen, oxygen, magnesium, silicon, iron, all the elements that stars have created over the history of the universe and that supernovae have spilled out into the wider cosmos. The intergalactic medium is therefore not pristine. It carries the chemical history of every galaxy that has ever existed. It is also almost entirely ionized. The hydrogen atoms in the intergalactic medium are not whole, they are protons that have been stripped of their electrons, drifting alongside free electrons through the wider space. The same is true of the helium and the heavy elements. They are bare nuclei wandering through a sea of free electrons. The medium is a plasma. And it has been a plasma for most of the universe's history, because long ago, the first stars and the first quasars filled the universe with ultraviolet light, and that ultraviolet light was energetic enough to ionize the hydrogen everywhere. The intergalactic medium has been kept ionized ever since by the combined ultraviolet output of all the stars and quasars in the universe. The temperature of the medium varies. Some of it is at roughly 10,000 Kelvin, the lowest temperature consistent with the ionization. Some of it is much hotter, at hundreds of thousands or even millions of Kelvin, especially in regions where galaxies have ejected hot winds, or where filaments of cosmic web matter have shock-heated as they fell together. Astronomers sometimes divide the intergalactic medium into phases by temperature. The cooler phase, at around 10,000 Kelvin, is sometimes called the Lyman alpha forest gas, because its absorption signature in distant quasar spectra appears as a forest of narrow absorption lines at the characteristic wavelength of hydrogen. The hotter phase, at hundreds of thousands to a few million Kelvin, is sometimes called the warm-hot intergalactic medium, and it is much harder to detect because it does not absorb visible or even ultraviolet light strongly. It only shows up in X-ray absorption studies. The Lyman alpha forest is one of the strangest and most beautiful objects in observational astronomy. When you look at the spectrum of a distant quasar, you see a smooth, bright continuum of light covering many wavelengths. But threaded through that continuum is a dense pattern of narrow absorption lines, each one slightly displaced from the others. Each line is the fingerprint of a small cloud of neutral hydrogen in the intergalactic medium, somewhere between the quasar and the telescope. The wavelength of each line is shifted by the expansion of the universe. The further away the cloud is, the more its absorption line is shifted toward redder wavelengths. So the forest of lines is also a map of the universe along that line of sight, with each absorption feature corresponding to a particular distance and a particular epoch. When astronomers look at quasars at different positions in the sky, they see different forests. By stacking and comparing these forests, they can reconstruct the three-dimensional structure of the intergalactic medium across enormous volumes of the universe and across enormous spans of time. The forest is a kind of cosmic tomography. It is one of the patient ways the universe lets itself be read. There is nothing dramatic about it. The information emerges slowly, line by line, sightline by sightline. And the picture that emerges is one of a vast, slowly evolving web of filaments and voids, with the intergalactic medium pooled along the filaments and thinner in the voids. If you stood in a random spot in the intergalactic medium between the Milky Way and Andromeda, what would you experience? Almost nothing. The light around you would come almost entirely from distant galaxies and quasars, and from the faint glow of the cosmic background. The temperature would be a thermodynamic abstraction. There would be far too few particles to transfer any meaningful heat to you. The particles themselves would pass through your immediate volume slowly, 1 or 2 protons every second, perhaps an occasional ion of helium, very rarely a heavy atom of oxygen or carbon. The density of cosmic rays would be low. The density of photons would be dominated by the cosmic microwave background. You would be in a place that is, by every laboratory measure, almost empty, and yet, by cosmic measure, almost full. Almost everything is somewhere in between. the intergalactic medium also has structure in motion. The whole thing is not stationary. It moves, slowly, along the gravitational potential of the cosmic web. Gas flows out of voids and into filaments, and along filaments toward galaxy clusters, and from there into individual galaxies. The intergalactic medium is the slow circulatory system of the universe. It carries matter from where it formed in the early universe to the places where it eventually becomes part of stars and planets, and, after the long life of those stars, returns to the intergalactic medium again to begin another cycle. Your atoms have already taken part in this circulation. The hydrogen in your body was, for most of cosmic history, somewhere in the intergalactic medium, drifting slowly through the cosmic web, on its way to becoming part of the cloud that became the sun and the earth, and, in time, you. It has been a long journey for those atoms, and the intergalactic medium is one of the places they paused for the longest stretches. The intergalactic medium is also where the cosmic web is most clearly visible. The web itself is made of dark matter, but the intergalactic gas traces it. Filaments of dark matter pull gas along their length. Sheets and walls of dark matter gather sheets and walls of gas. Voids of dark matter contain voids of gas. By mapping the intergalactic medium through Lyman alpha forests, through warm-hot intergalactic medium absorption, through the slow gravitational lensing of background light, astronomers map the cosmic web. The web is the deepest scaffolding of the universe, and the intergalactic medium is its faintly luminous skin. There is also a magnetic field threading through the intergalactic medium, though it is extraordinarily weak. The strength of the intergalactic magnetic field is measured in nanogauss, a billionth of a unit. In some regions, it may be even weaker than that. The Milky Way's own magnetic field is on the order of microgauss, 1,000 times stronger. Earth's surface magnetic field is hundreds of thousands of times stronger again. The intergalactic magnetic field is so weak that no compass on Earth would respond to it. And yet it is there, and it does something. It shapes the paths of cosmic rays. It influences the propagation of charged particles across cosmic distances. It may even slowly amplify itself over billions of years as it interacts with the slow flows of gas along the cosmic web. The intergalactic medium is also the medium across which cosmic rays travel. Some cosmic rays are produced inside galaxies and never leave them. Others are accelerated by the central black holes of distant galaxies and propagate outward into intergalactic space, sometimes with enormous energies. The most energetic cosmic rays in the universe, those with energies far beyond anything any laboratory has ever produced, travel intergalactic distances before reaching Earth. As they travel, they interact slowly with the cosmic microwave background, losing energy little by little, until eventually they fall below a certain critical energy, known as the cosmic ray cutoff. The intergalactic medium is therefore not only a medium for matter, it is also a slow filter for the highest energy particles in the universe. If you stayed long enough, in the intergalactic medium long enough, being measured in millions or billions of years, you would notice that it changes. The expansion of the universe is slowly pulling the medium apart, thinning it further, lowering its density over deep time. The galaxies on either side of the gap, the Milky Way and Andromeda, are gravitationally bound to each other and resist this expansion locally. They will not be pulled apart from each other. But beyond the local group, the more distant galaxies are slowly receding, and the intergalactic medium between them is being stretched along with them. In the deepest future, the intergalactic medium will become even more diffuse than it is today. The universe will become a slightly emptier place, slowly, across the deep time still ahead. For now, though, the medium is here. It is between us and Andromeda, threaded with filaments, lit faintly by the absorbed light of distant quasars, glowing very softly in X-rays where it has been heated by gravitational infall and galactic winds. It is the place where most of the ordinary matter in the universe is. It is the place your atoms came from. It is the place your atoms will return to when the long life of the Sun is finally over and Earth's chemistry is dispersed into the wider galaxy and then, eventually, into the wider cosmos. There is nothing dramatic about this. The intergalactic medium is patient. It moves slowly. It changes slowly. It does not announce itself. Like much of what is most fundamental about the universe, it is easy to overlook. But it is also the medium through which everything else moves, and it deserves to be noticed, gently, even if only for the brief span of a single sleepy hour. It is the soft sea you and the Milky Way and Andromeda all drift in together, and it has always been here. Even in the middle of the intergalactic medium, far from any galaxy, you would not be in complete darkness. There is a faint, ancient light that fills every cubic meter of the universe, a glow so soft and so uniform that you would not notice it without instruments designed to detect it. This light is older than every galaxy, every star, every planet. It is older than the chemistry of any element heavier than the lightest few. It is the oldest light in the universe, and it is everywhere at once. Astronomers call it the cosmic microwave background. The story of this light is a quiet one. It was created when the universe was about 380,000 years old, a tiny fraction of the universe's current age, but already old enough that the universe had cooled enough for atoms to form. Before that moment, the universe was hot, dense, and full of charged particles. Electrons and protons could not bind into neutral atoms because the temperature was too high. Light could not travel freely because it was constantly scattering off the charged particles, much the way light bounces inside a fog. The universe in those first few 100,000 years was opaque, full of light, but unable to let it through. Then the universe cooled past a critical threshold. The temperature dropped to a few thousand Kelvin. Electrons and protons could finally combine into neutral hydrogen atoms without being immediately ripped apart again. The fog cleared. The light that had been bouncing endlessly through the charged plasma now had nothing to bounce off. It traveled freely. And it has been traveling freely ever since, for more than 13 billion years. Slowly redshifted by the expansion of the universe from its original visible glow into the microwave wavelengths we detect today. The temperature of this ancient light, as it reaches us now, is about 2.7 Kelvin. That is just a few degrees above absolute zero. It is colder than the coldest natural temperatures anywhere on Earth, colder than the surface of Pluto, colder than almost anything you might imagine. And yet, it is everywhere. Every cubic centimeter of the universe contains about 400 photons of this ancient light. There are more photons of the cosmic microwave background in any small volume of intergalactic space than there are atoms in that same volume. The microwave background is, in number, the most populous thing in the universe. It is also extraordinarily uniform. When astronomers map its temperature across the entire sky, they find that it is the same in every direction, to about 1 part in 100,000. The variations are tiny temperature differences of microkelvin against a background of 2.7 Kelvin. But those tiny variations are some of the most important measurements in cosmology. They are the seeds from which everything else grew. Every galaxy, every cluster, every filament of the cosmic web, every void, all of them grew out of those microscopic variations in the early universe. Gravity slowly amplified the denser regions, pulling more matter inward over billions of years, until the dense regions became galaxies and the less dense regions became voids. The cosmic microwave background is the snapshot of the universe at the moment those seeds first became visible. Everything that has happened in the universe since then is, in some sense, a slow unfolding of the patterns that were already there. When you stand in the intergalactic medium between the Milky Way and Andromeda, the cosmic microwave background is around you. It comes from every direction. You cannot point to any particular source of it. It is the light of the early universe, stretched and cooled, and it has been with you all along. It is the soft warmth, though almost no warmth, given how cold it is, that fills the space around you. It is the light that does not come from any star, but from everywhere at once. It is, in a quiet sense, the original light. Every other photon in the universe was created later by some star or quasar or galaxy or atomic reaction. The cosmic microwave background is the photon that was there first. It also bathes everything else in the universe. The intergalactic medium drifts in it. The galaxies drift in it. The dark matter halos drift in it. Your body, in its small, slow way, is drifting in it. If you were able to filter out all the other light in the night sky, the starlight, the galactic light, the light pollution from cities, and you were able to use a sensitive enough detector to see only the cosmic microwave background, you would see a soft, uniform glow filling the entire sky in every direction, the same shade everywhere. It would look like a single soft surface surrounding you, equally far in every direction. That surface is called the surface of last scattering, and it is the wall of the observable universe, the place beyond which we cannot see, because beyond it the universe was opaque and no light could escape. The cosmic microwave background also carries another piece of information that becomes relevant on this kind of journey. Because it is so uniform, any motion you have relative to the universe as a whole shows up as a slight asymmetry in the temperature of the background, slightly warmer in the direction you are moving, slightly cooler in the direction behind you. This is called the dipole. The Earth, the Sun, the Milky Way, and the local group all move relative to the cosmic microwave background, and each motion shows up as a contribution to the dipole. The local group as a whole is moving toward a region of higher density called the Great Attractor at roughly 620 kilometers per second. The Milky Way moves within the local group at its own pace. The Sun moves within the Milky Way at its own pace again. The Earth orbits the Sunday. The cosmic microwave background is the great reference frame against which all of this motion can be measured. It is the closest thing the universe has to an absolute rest frame, though it is not really absolute, only ancient. So as you drift through the intergalactic medium between the Milky Way and Andromeda, the ancient light is around you, and your motion through it is recorded invisibly in your shifted temperature in different directions, in the slight blue shift ahead of you and the slight red shift behind. You are moving through the background, the same way the Sun and the Earth and the local group are moving. The background does not push back. It simply is. And it remembers, in the soft way that uniform fields can remember, the geometry of the very early universe, before any star had formed, before any galaxy had assembled, before any of the structure of the cosmos had begun to take shape. The microwave background also gives the intergalactic medium a tiny floor temperature. Even in the deepest void, where there is essentially no other source of energy, the temperature cannot fall below the temperature of the cosmic microwave background, because the background fills every volume and keeps everything at least slightly warm. As the universe continues to expand, the cosmic microwave background will continue to cool. In hundreds of millions of years, it will be slightly cooler. In billions of years, it will be cooler still. Eventually, in the deep future, it will cool to fractions of a Kelvin, and then to thousandths of a Kelvin, and then below detectability for any ordinary instrument. The universe will continue to grow colder and quieter, and the ancient glow will fade into the long, deep silence ahead. But for now, in our era, it is warm enough to feel, in a thermodynamic sense, and it fills the space between the Milky Way and Andromeda, along with everything else. There is another aspect to the cosmic microwave background that is worth holding gently in mind during this journey. It is the light of the very young universe, but it is reaching us now. The photons currently bathing the intergalactic medium have been traveling for almost the entire age of the universe. They were emitted when the universe was 380,000 years old. They have been traveling for more than 13 billion years. They will continue to travel onward into the future. The cosmic microwave background is, in some ways, the longest traveling thing in existence. It has been crossing the universe since before anything else was here to do so. When astronomers measure the small variations in the cosmic microwave background, they find faint hints of every later structure already present in the seeds. The slightly warmer spots correspond to slightly denser regions, which would later collapse to form galaxy clusters. The slightly cooler spots correspond to slightly less dense regions, which would later become voids. The local group itself, the family containing the Milky Way and Andromeda, is the descendant of one of these soft, early-density seeds. The galaxies you came from and the galaxy you are moving toward both grew from variations imprinted on the cosmic microwave background more than 13 billion years ago. The two galaxies you are crossing between are, in a sense, two small details in a much older pattern. This is a quiet kind of perspective. The local group did not just appear. It grew, slowly, out of a small overdensity in the very early universe. The whole shape of where you are tonight was set down long before any star existed. The journey you are imagining, the gap between the two galaxies, the soft, layered crossing, the dark matter bridge, all of it traces back to a tiny initial fluctuation in the seeds of structure that the cosmic microwave background still carries. The deepest reason there is a Milky Way and an Andromeda and a gap between them is recorded very faintly in the temperature of the soft ancient glow. And the soft ancient glow is here, tonight, around you, around the imagined traveler, around the Earth, around the Sun, around every cubic meter of the universe. It is the slowest weather. It is the oldest light. It is the calm presence that has been there since before anything else could see. There is no need to do anything with it. It is just there. Above it, behind it, around it, the next great structure of the journey waits the structure that the cosmic microwave background seeds eventually grew into. The cosmic web is gentle, ancient, and enormous, and it is the scaffolding on which the local group and every other family of galaxies is hung. The Milky Way and Andromeda do not face each other across an empty gap. They face each other across a small, slow, gravitationally bound family of galaxies, all of which share the same general region of space, all of which influence each other's motion, and all of which together form a quiet structure called the local group. To cross from the Milky Way to Andromeda is to walk through the middle of this family. The journey is shared territory with about 80 other galaxies, some of them small and faint, some of them bright and prominent, all of them old companions of the larger spirals. The local group is one of the smaller galactic families. It is not a cluster, in the way that the Virgo cluster or the Coma cluster is. Those are densely packed associations of hundreds or thousands of galaxies. with strong central concentrations and hot intracluster gas. The local group is much gentler than that. It has only about 80 known members, and most of them are very small. The three large spirals, the Milky Way, Andromeda, and the Triangulum Galaxy, dominate the family by mass. Everything else orbits one of those three, or drifts through the local group on long looping paths that may or may not eventually be captured by one of them. The local group's diameter is about 10 million light-years. That is a significant volume of space, far larger than the distance between the Milky Way and Andromeda alone. The two large spirals are not at the edges of the local group. They are near the center, with the Triangulum Galaxy a few million light-years off to one side. The total mass of the local group is roughly 2 trillion solar masses, most of it in dark matter rather than visible stars. The family is gravitationally bound, that is, the galaxies in it will not be pulled apart by the expansion of the universe. They will stay together, drifting and merging and reshaping each other for as long as the universe continues to exist. Each large spiral has a court of smaller companions. The Milky Way has dozens of dwarf galaxies orbiting it. The two brightest are the Large Magellanic Cloud and the Small Magellanic Cloud, which can be seen with the naked eye from the southern hemisphere of Earth as faint patches of light. They are not, in fact, clouds. They are small galaxies, irregular in shape, full of young blue stars and old red ones. The Large Magellanic Cloud holds about 10 billion stars. The Small Magellanic Cloud holds a few billion. Both galaxies are slowly being pulled apart by the Milky Way's gravity. Over the next few billion years, both will be torn into long streams of gas and stars, and eventually, their material will be absorbed into the Milky Way's disk. They will become part of the Milky Way's own population, mixing with the older stars and adding their own contribution to the slow chemistry of the galaxy. The Sagittarius dwarf galaxy is another companion, much fainter than the Magellanic Clouds. It is currently being torn apart by the Milky Way and has left a long stream of stars across the halo. From its remains, astronomers have learned a great deal about how small galaxies are absorbed into larger ones. The Canis Major dwarf is even closer and even more disrupted. There are also fainter, more distant companions: Draco, Ursa Minor, Sculptor, Fornax, Carina, Leo I, Leo II, and many others, each containing only a few thousand to a few million stars. They orbit the Milky Way on long, slow paths, taking hundreds of millions or billions of years to complete a single orbit. Some are old companions that have been around since the Milky Way first assembled. Others are more recent captures from the outer local group. Andromeda has its own court of companions, similarly varied. The two brightest are Messier 32 and Messier 110, both visible as small bright patches near Andromeda in long-exposure photographs. Messier 32 is a compact elliptical, very dense, with a small bright core. It is sometimes thought to be the remnant of a larger galaxy that has been mostly consumed by Andromeda. Messier 110 is a small elongated elliptical with a slightly tidally distorted shape. There are also dozens of fainter dwarf galaxies orbiting Andromeda, Andromeda 1, Andromeda 2, Andromeda 3, and so on, numbered in order of discovery. They are too faint to see without a telescope, and they orbit Andromeda the way the Milky Way's dwarfs orbit the Milky Way, on long looping paths. Between the two great spirals, drifting in the middle, are a handful of isolated dwarf galaxies that do not clearly belong to either. The Pegasus dwarf, the Wolf-Lundmark Melotte galaxy, and others wander through the in-between space, gravitationally bound to the local group as a whole, but not to either large spiral specifically. They are small, faint, and far apart, and they move slowly through the same shared territory that any traveler between the Milky Way and Andromeda would also cross. Somewhere in the middle of the gap between the two large galaxies, there is a point called the barycenter, the common center of mass, around which both spirals are slowly turning. The barycenter is not in the Milky Way, and not in Andromeda. It is between them, closer to Andromeda because Andromeda is slightly more massive than the Milky Way when dark matter is counted. The two great spirals are slowly orbiting this invisible point, the same way two stars in a binary system orbit a point between them. The orbital period is very long, measured in billions of years rather than years, because the masses are enormous and the distances are vast. But the motion is real. The two galaxies are not stationary with respect to each other. They are slowly falling toward each other, very slowly turning, very slowly closing the distance. The barycenter is also a kind of conceptual landmark. It is the place where you would feel the gravitational pull of both galaxies most evenly, the place where neither one is more clearly the home. If you stopped your imaginary journey at the barycenter and looked around, you would see the Milky Way as a soft patch of light in one direction, and Andromeda as a soft patch of light in the other. They would appear almost the same size in the sky, like two great wheels facing each other across the middle of a vast room. Between them would be smaller, scattered points of light from the other local group members. And around all of it would be the deep darkness of the intergalactic medium and the cosmic web beyond. Threaded through the local group are several streams of gas and stars that mark the histories of past interactions. The most famous is the Magellanic Stream, a long ribbon of hydrogen gas that trails behind the Magellanic Clouds as they orbit the Milky Way. The stream is hundreds of thousands of light-years long. It extends across more than half the sky, as seen in radio observations of hydrogen. It is gas that was tidally stripped from the Magellanic Clouds by their encounters with the Milky Way and with each other, and it now stretches in a long arc through the Milky Way's halo, slowly falling inward over hundreds of millions of years. Eventually, most of this gas will become part of the Milky Way's disk, where it will form new stars. The stream contains roughly 2 billion solar masses of hydrogen-enough material to form several large open clusters or to add a significant new pulse of star formation to the galaxy. Similar streams exist around Andromeda. The most prominent is the Andromeda Giant Stellar Stream, which loops around Andromeda's southern half and contains the remains of a small galaxy that was torn apart by Andromeda's gravity in the distant past. Other streams in Andromeda's halo trace the trajectories of other absorbed companions. The streams record a slow history of cannibalism. Both large spirals have been eating their smaller neighbors for billions of years, and the streams are the lingering ghosts of those meals. The local group also has a shared gas reservoir that extends through the in-between space. This is the warm gaseous halo that connects the circumgalactic medium of the Milky Way and the circumgalactic medium of Andromeda. Some of the gas in this reservoir is local. It belongs to one galaxy or the other. Some of it is shared. It has been in the in-between for so long that it cannot be assigned to either galaxy specifically. It is the breath of the local group, slowly cycling between the two large hosts and the smaller members. When you stand in this in-between, then, you are not in a void. You are in the shared atmosphere of a family. You are surrounded by the slow gravitational embrace of two great spirals and their smaller companions. You are bathed in the ancient microwave background of the early universe. You are drifting through gas that has been here for billions of years and will be here for billions more. You are surrounded by motion that is too slow to notice but is real, and by structure that is too sparse to see but is everywhere. You are in the middle of the most familiar small family in the universe, and the family is older than human history by a very wide margin. The local group is one of many such families. There is the Sculptor group, not far away, with the Sculptor galaxy at its center. There is the Maffei group, hidden behind the dust of our own galactic disk. There is the Centaurus A and Messier 81 group, with its peculiar galaxy at the center, and the Canes Venatici I and II groups beyond. Each of these is a small family of galaxies bound by their own gravity, each of them drifting through the wider intergalactic medium on its own slow journey. Together, these nearby groups form a small association of family groups, which in turn is part of the larger Virgo supercluster, which in turn is part of Laniakea, and so on outward in nested rooms. But for the journey at hand, the local group is the immediate neighborhood. It is where the journey takes place. To go from the Milky Way to Andromeda is to walk across the home territory of this small family, to pass through the soft outer halos of two great spirals and the orbits of dozens of their companions, all of them moving together, all of them gravitationally tied to each other, all of them quietly aging in the deep, gentle dark. You are in their company throughout the crossing. The family is around you. The dark is filled with their gravity, even when you cannot see them. They are not separated from you by anything except distance and time. And both of those, in the patient way of the cosmos, are not really separations at all. They are just slow forms of company. There is one more layer of structure to walk through, and it is the largest of all. The local group is not alone. It is part of a web, a vast, slow, gravitational fabric that spans the entire universe. The cosmic web is the largest known structure in nature. It is the place where every galaxy lives, the place where every cluster sits, the place where every void rests. The Milky Way and Andromeda are two small, bright details in a structure that extends far beyond anything imaginable from inside a single galaxy. The cosmic web is built out of dark matter, traced by gas and decorated with galaxies. Most of its mass is invisible. Most of its volume is empty. And yet it has a clear shape, and that shape has been mapped patiently across decades by combining the positions of millions of galaxies, the absorption signatures of intergalactic gas, and the gravitational lensing of background light by foreground matter. The picture that emerges is a kind of foam, a three-dimensional network of long, thin filaments, with denser clumps where filaments cross, and vast, nearly empty regions filling the spaces in between. Filaments are the main feature. They are long, thin, mostly invisible concentrations of dark matter, with intergalactic gas pulled along them by gravity, and with galaxies dotted along their length like beads on a string. Most galaxies live on filaments. The Milky Way is on one. Andromeda is on the same one, or perhaps on a closely related one that connects to it. The filament our local group inhabits is part of the larger network of filaments that fills the local universe. It threads through nearby galaxy groups, including the Sculptor group, the Maffei group, and others, on its way to a more crowded region called the Virgo cluster. Where filaments intersect, you get nodes, dense regions of higher mass, often containing galaxy clusters at their cores. The Virgo cluster, about 55 million light-years from Earth, is the nearest large node. It contains more than 1,000 galaxies, with a single giant elliptical galaxy at its center. Surrounding the Virgo cluster, in roughly all directions, is a wider, less dense structure called the Virgo supercluster, an extended association of groups, including the local group, all loosely organized around the Virgo cluster as their gravitational center. The Virgo supercluster is about 100 million light-years across, and it contains many thousands of galaxies. The Virgo supercluster, in turn, is just a small piece of a much larger structure called Laniakea. Laniakea is about 500 million light-years across, and it contains roughly 100,000 galaxies. It is defined not by a sharp boundary, but by the gravitational flow of galaxies. Every galaxy inside Laniakea is being drawn toward a common gravitational center known as the Great Attractor, deep in the constellation Centaurus. The local group, the Virgo cluster, and a great many other galaxy groups are all flowing slowly toward this center at speeds of hundreds of kilometers per second. The flow is not visible directly. It can only be measured by carefully comparing the recession velocities of galaxies and accounting for the expansion of the universe. What remains, after the expansion is subtracted, is the peculiar flow toward the Great Attractor. Beyond Laniakea, the cosmic web continues. There is the Perseus-Pisces supercluster, the Coma supercluster, the Hercules supercluster, the Shapley supercluster, and many others, each with its own internal structure of clusters, groups, and individual galaxies. The Shapley supercluster, behind the Great Attractor, is one of the most massive nearby superclusters and may itself be drawing Laniakea toward it on a longer timescale. Between the superclusters are the void's vast, mostly empty regions where there are very few galaxies and where the intergalactic gas is even thinner than average. The voids are some of the most quietly striking features of the universe. The Boites void is one of the largest known nearby voids, with a diameter of about 330 million light-years. It contains only a small number of galaxies, far fewer than a comparable volume of less empty space would contain. There are similar voids elsewhere, the local void, the Eridanus supervoid, and many others. Some astronomers have suggested that the Milky Way itself sits inside a larger underdensity called the KBC void, which would help explain certain peculiarities of the local Hubble flow. Whether or not that suggestion is fully correct, it is true that the universe is shaped much more by its voids than people often imagine. Voids occupy somewhere between 60 and 80% of the universe's total volume, while containing only about 10% of its galaxies. The universe is mostly empty, in a way that is gentler and more spacious than any other description can quite capture. The cosmic web is also slowly evolving. The structures we see today did not always exist. They grew over billions of years out of small density fluctuations in the early universe. Gravity slowly amplified the denser regions, pulling more matter inward, while the less dense regions slowly expanded outward with the general expansion of the universe. Over time, the dense regions became filaments and nodes. The less dense regions became voids. The web is the shape the universe has been assembling for 13 billion years. It is still assembling. The filaments are still being threaded. The nodes are still gathering more mass. The voids are still growing emptier as the universe expands and the matter between them flows away to denser regions. From inside the Milky Way, the cosmic web is invisible. The night sky, even on the darkest night, only shows you the stars of your own galaxy and a faint smudge of Andromeda. The cosmic web is too large and too sparse and too dark to be seen by eye. But it is everywhere around you. Every direction you look, you are looking outward through the local filament, past the local group, through the surrounding galaxy groups, and into the larger superclusters and voids beyond. The light from distant galaxies, when properly measured, reveals the underlying scaffolding. The patient long-looking of cosmic surveys has, over the past several decades, traced out the local web in considerable detail. The galaxies we see are the bright details. The web is the structure they are arranged on. For the journey between the Milky Way and Andromeda, the cosmic web matters in a quiet way. The two galaxies are not just neighbors. They are part of the same local node of the web. The dark matter filament that connects them is part of the larger network. The intergalactic gas you would drift through on the way from one to the other is the local gas of this filament, pulled by gravity along its length. The structure you cross is a small piece of the cosmic web's overall geometry. And every galaxy you would see along the way, every dwarf, every distant spiral, every faint smudge in the background of the night sky, is part of the same scaffolding. It is a calming structure in its own way. The universe is not random at the largest scales. It is patterned. The patterns are vast and slow and mostly invisible, but they are real. Galaxies are not scattered uniformly throughout space. They are concentrated along the filaments. The local group is not floating alone in a featureless ocean. It sits on a filament that joins it to a larger family of groups, which in turn joins a larger supercluster, which in turn joins still larger structures. Every galaxy has a place. Every cluster has a place. Every void has a place. The shape is gentle, but it is there. Sometimes, when people learn about the cosmic web for the first time, they find it strange. It can feel like the universe has too much structure to be random and not enough structure to feel familiar. But after a while, the strangeness softens. The web is just the slow result of gravity working on small seed variations over 13 billion years. The seeds were already there, in the cosmic microwave background. Gravity has been amplifying them ever since. The web is what the universe naturally becomes, given enough time. The local group is what one small region of those seeds naturally became, given the same time. The Milky Way and Andromeda are what two small subregions of that local region naturally became, given still more time. To stand in the intergalactic medium between the Milky Way and Andromeda, in the soft glow of the cosmic microwave background, on the shared filament of the local cosmic web, is to stand at one tiny point in a vast, slow architecture. The architecture has been building itself since long before any star existed. It will continue building itself long after any star has burned out. The local group is part of this larger architecture. The local group itself contains the two galaxies you are between, and the two galaxies you are between are themselves the products of the same patient gravitational accumulation. You are not in an alien place. You are in a soft middle layer of a structure that includes you and includes everything around you. The web extends much further than you can ever see, of course. The observable universe, the volume of space whose light has had time to reach us in the age of the cosmos, is about 93 billion light-years across. The actual universe may extend much further. Within the observable volume, there are roughly 2 trillion galaxies, each on its own piece of filament or sitting in its own corner of a cluster, each with its own complicated journey through deep time. The Milky Way and Andromeda are just 2 of those galaxies, on one of those filaments, in one of the smaller groups, in one of the smaller superclusters, in one of the smaller portions of the universe. There are so many other places, and yet this is the place. This is where the journey is happening. This is where the long drift between 2 soft spirals takes place. And so, after passing through the Milky Way's atmosphere and dark matter halo, after drifting through the intergalactic medium, after bathing in the ancient glow of the cosmic background, after moving among the smaller members of the local group, and through the soft filament that links the 2 large hosts, you would at last begin to feel the gentle pull of the other side. The far side. The destination. Andromeda would not appear as a sudden landmark. It would slowly become a bigger and bigger presence in the sky, growing from a faint patch into a great wheel of light. The atmosphere of the other galaxy would close in around you. The dark matter halo would take over from the Milky Ways. The long crossing would begin to end. There would still be many great distances to cover. The journey from the outer edge of Andromeda's dark matter halo to the heart of Andromeda's disk would be hundreds of thousands of light-years more, slow and patient. But the long stretch of the in-between would be behind you. You would have crossed the soft sea between two galaxies. You would have done it slowly, the only way it can be done. And the other galaxy would be ready to meet you in the same soft, layered way the Milky Way let you go. Almost nothing made by human hands has even left the solar system, let alone the galaxy. The deepest human reach into space is a small handful of spacecraft drifting outward through the local interstellar medium. None of them headed anywhere in particular, all of them so slow on the cosmic scale that they will not pass within hundreds of light-years of another star for tens of thousands of years. And yet, while human probes have barely begun the journey between galaxies, the universe itself has been making intergalactic crossings constantly throughout its history. Light, particles, gravitational waves, and rare objects all cross intergalactic space all the time. We are not the first travelers. We are not even the smallest ones. Light is the great traveler. Every galaxy in the universe emits light, and that light fills the intergalactic medium with a faint, continuous, multispectral bath of photons. The light of Andromeda has been crossing the gap to the Milky Way for 2.5 million years. The light of more distant galaxies has been crossing for hundreds of millions, billions, sometimes over 13 billion years. The intergalactic medium is constantly filled with the light of every galaxy, traveling in every direction. The cumulative effect of all this light is a faint cosmic background, not just the microwave background, but a much fainter cosmic optical background and cosmic infrared background, the integrated light of every galaxy that has ever existed, blended together. It is too faint to see by eye, but it is there. The universe glows softly at every wavelength, almost everywhere, all the time. Photons travel forever, in principle, unless something absorbs or scatters them. The intergalactic medium is so thin that very few photons get scattered or absorbed on their way between galaxies. The light of Andromeda reaching Earth tonight is essentially the same light that was emitted from Andromeda 2.5 million years ago, slightly dimmed by inverse square geometry, but otherwise intact. The intergalactic medium is mostly transparent. That is one of the gentle reasons distant galaxies are visible at all the universe lets their light through, almost without interruption. Beyond visible light, there are also other forms of travel. Cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated by violent processes in stars, supernovae, neutron stars, and the central black holes of galaxies propagate through the intergalactic medium too. The lower-energy cosmic rays are mostly trapped inside galaxies by galactic magnetic fields. The highest-energy cosmic rays, the ones with energies that are difficult even for the largest particle accelerators on Earth to match, can escape their host galaxies entirely and travel intergalactic distances. They follow the intergalactic magnetic field lines loosely, deflected only slightly by the very weak intergalactic magnetic field. As they travel, they interact slowly with the photons of the cosmic microwave background. The interactions are rare, but over millions of light-years of travel, they add up. Above a certain energy threshold, cosmic rays lose energy faster than they can be replenished by their travel. and this defines a kind of upper limit on the energies that can reach us from distant sources. The intergalactic medium is thus a slow filter, allowing most cosmic rays to pass, but gently degrading the most energetic ones. Neutrinos are another kind of intergalactic traveler. They are nearly massless, nearly non-interacting particles. They are produced by nuclear reactions in stars, by stellar explosions, by interactions in the central regions of active galactic nuclei, and by other extreme processes. Once produced, they travel almost completely undisturbed through whatever matter they encounter. A neutrino can pass through a light-year of solid lead with only a small probability of being absorbed. It can pass through entire galaxies effortlessly. The intergalactic medium is no obstacle to a neutrino at all. Astronomers have detected neutrinos from sources in our own galaxy and from supernovae in nearby galaxies, and in the past decade or so they have begun to detect high-energy neutrinos from sources in distant galaxies, including some that appear to come from blazars and other active galactic nuclei. The intergalactic medium is therefore also constantly bathed in a faint flux of neutrinos traveling between galaxies, extraordinarily difficult to detect, but real. Gravitational waves are another way the intergalactic medium is crossed. When two neutron stars merge, when two black holes spiral together, when an extremely massive star collapses, the resulting events send out ripples in space-time that propagate outward at the speed of light. Those ripples cross intergalactic space the same way light does, almost without interference, almost without dimming, except by simple geometric spreading. The first gravitational waves ever detected came from a black hole merger more than 1 billion light-years away. The waves had been traveling for more than 1 billion years before they reached the instruments on Earth that finally registered them. The intergalactic medium is constantly threaded with gravitational waves from such events all over the universe, though most of them are too faint to detect with current instruments. The universe is not silent at the level of space-time. It is full of gentle ripples that have been crossing intergalactic space since long before there was anyone here to listen. Beyond light, cosmic rays, neutrinos, and gravitational waves, there are also rare physical objects that cross intergalactic space. Hypervelocity stars are stars that have been ejected from their host galaxies by close encounters with central supermassive black holes. A small number of such stars are known. They are traveling at hundreds or thousands of kilometers per second relative to their host galaxies, fast enough, in some cases, to escape the host's gravity entirely. Once they have escaped, they drift through intergalactic space on long, unbound trajectories. The number of hypervelocity stars is small in any one galaxy, but across the universe, the total population is significant. There are likely millions of such stars in the intergalactic medium of the local group alone, though they are extremely difficult to detect because they are so far from any host galaxy. There are also intergalactic stars, stars that have been torn out of their host galaxies during galactic mergers and now drift through intergalactic space far from any galaxy. These are different from hypervelocity stars in that they were not ejected by a single dramatic event. They were tidally stripped from a galaxy that came too close to another galaxy. The local group is too quiet right now to have many such stars, but galaxy clusters, like the Virgo cluster, where galaxies are constantly interacting with one another, are full of intergalactic stars. In the Virgo cluster, perhaps 10 to 20% of all the stars are not part of any individual galaxy. They are drifting through the intra-cluster space, the gentle leftovers of countless past mergers. Across the universe, the number of such stars may be in the tens or hundreds of billions, though their density per cubic light-year is exceedingly low. There are also intergalactic globular clusters, small bound systems of old stars that have somehow ended up in the gaps between galaxies. A few of these have been observed in nearby galaxy groups. They are very rare per unit volume, but they exist. They may have been the central remains of small dwarf galaxies that were stripped of their outer regions by tidal forces. They are like dim islands in the in-between, very faint and very small but real. There are also occasional dwarf galaxies that wander through the in-between space, gravitationally tied to the local group as a whole, but not orbiting either of the two large spirals specifically. Some of these may eventually be captured by one of the larger galaxies. Others may drift through the local group on long looping paths for billions of years before being absorbed. Finally, there are the small human-made things. The two Voyager probes, the two Pioneer probes, and the New Horizons probe are the deepest human reach into space. Voyager 1 is currently the most distant human object, about 165 astronomical units from Earth, well past the heliopause and into the interstellar medium of the Milky Way. The probes are traveling at roughly 17 kilometers per second on average. At those speeds, they will not reach the nearest star for tens of thousands of years. They will not reach Andromeda for many billions of years, and even if they were pointed in Andromeda's direction, they would not arrive in any meaningful sense. They are interstellar travelers, but they are not, even nominally, intergalactic travelers. The radiosphere is another small human signature. Every radio broadcast Earth has ever transmitted has spread outward at the speed of light, forming an expanding sphere of human radio noise around the Earth. The sphere is currently about 100 light-years across. That is a small fraction of the Milky Way's diameter and a vanishingly small fraction of the distance to Andromeda. By the time the radiosphere reaches the outer edge of the Milky Way's stellar disk, it will be tens of thousands of years from now. By the time it reaches Andromeda, it will be more than 2 million years from now, and the signal will have weakened far below any detection threshold, even for a hypothetical advanced listener. So, the human contribution to the intergalactic crossing is small. We have not really begun, but the universe has been crossing this distance with light and particles and waves for billions of years, and the crossing continues every moment, in every direction, at every wavelength. The intergalactic medium is, in this sense, the most heavily trafficked region in the universe. Nothing else is so constantly threaded by signals from so many sources. It is the great corridor through which the universe communicates with itself. There is something quietly wonderful about that. The space between galaxies looks empty, but it is full of slow conversation. Andromeda sends its light to the Milky Way. The Milky Way sends its light to Andromeda. Both galaxies send light to every other galaxy in the visible universe. Quasars send their light across billions of light-years to be absorbed by hydrogen clouds along the way. Black hole mergers send their gravitational waves across cosmic distances to be received by patient instruments. Neutrinos from distant supernovae arrive at Earth every day, almost all of them passing through without interaction, but a tiny few of them registering on the instruments designed to listen for them. The intergalactic medium is the medium of all these conversations. And the conversations are slow. A photon emitted by Andromeda 2.5 million years ago is only just now arriving. By the time the photon arrives, the source has already moved a small distance. Andromeda has approached the Milky Way by another 270,000 light-years worth of motion, though that is small compared to the gap. The conversation is not real time. It cannot be. The universe is too large for real time. Everything is, in some sense, news from the past. And yet the news arrives anyway, faithfully, photon by photon, particle by particle, ripple by ripple, never quite stopping. It is a soft kind of company. The intergalactic medium is never truly empty, never truly silent, never truly without traffic. The universe is patient enough to fill even the largest gaps with slow communication. And in the middle of the gap between two great spirals, you would be in the middle of all of it, receiving light from the galaxy ahead, light from the galaxy behind, light from every distant source the universe has to offer, and the ancient microwave background underneath everything. You would be in the middle of a quiet, vast, ongoing exchange that has been going on for 13 billion years and shows no sign of slowing. The journey from one galaxy to another, in this sense, is just one more form of slow communication. You are crossing the corridor that everything else uses too. And the corridor is wide, and the corridor is patient, and the corridor is, in its quiet way, never alone. Eventually, after the long crossing through the soft sea, the journey would begin to feel different. The intergalactic medium would still be around you. The cosmic microwave background would still be everywhere. The cosmic web would still be threaded faintly through the distances. But ahead, the gentle pull of the next galaxy would have grown into something noticeable. The dark matter halo of Andromeda would have folded around you. The gaseous atmosphere of Andromeda would have begun to thicken, and the great wheel of light at the center of your sky would have grown until it filled a substantial portion of your view. You would be entering the second galaxy. The first thing you would cross would be the outer reach of Andromeda's dark matter halo. Andromeda's halo, like the Milky Way's, extends roughly 1 million light-years in radius. The two halos likely overlap softly somewhere in the middle of the gap between the galaxies. So by the time you finally pass into the part of space that is more clearly Andromeda's than the Milky Way's, you would have crossed a long, gentle transition. Andromeda's dark matter halo is comparable in mass to the Milky Way's, perhaps slightly more massive when including all of its outer extensions and the influence of its larger total mass. The halo is invisible, but it is there. You would not feel anything as you crossed into it, just as you did not feel anything as you left the Milky Way's halo behind. Gravity does not announce itself. Inside the dark matter halo, you would begin to encounter the outer regions of Andromeda's gaseous halo, its circumgalactic medium. Andromeda's circumgalactic medium has been mapped through ultraviolet absorption studies, the same technique used for the Milky Way's atmosphere. Andromeda's atmosphere extends out to about 1 million light-years from the galaxy's center, with two main layers, an inner, denser layer, extending to roughly 150,000 light-years from the disk, and a vast, diffuse outer layer extending much further. The outer layer is the one that nearly touches the Milky Way's atmosphere in the middle of the gap. The inner layer is more concentrated, denser, and lies closer to the disk itself. Andromeda's atmosphere is composed of ionized hydrogen, ionized helium, and trace heavier elements, much like the Milky Way's. The temperatures span a wide range, from tens of thousands of Kelvin in the cooler outer parts to several million Kelvin in the hotter inner regions. There is a continuous cycle between the disk and the atmosphere, the same kind of slow fountain that the Milky Way has. Gas rises from Andromeda's disk into its atmosphere, cools, and falls back down again. Heavy elements forged in Andromeda's stars are mixed into the atmosphere and slowly return to the disk, enriching each new generation of star formation. The atmosphere is the slow chemical mixer of the galaxy, the same way the Milky Way's atmosphere is the slow chemical mixer of our galaxy. Inside the atmosphere, you would begin to encounter the outer stars of Andromeda's stellar halo. Andromeda's halo extends to at least 300,000 light-years from the galaxy's center, possibly further. The halo contains a population of old, metal-poor stars and roughly 500 globular clusters, about 3 times more than the Milky Way has. This is one of the genuine differences between the two galaxies. Andromeda's globular cluster system is much richer than the Milky Way's, with many large, luminous clusters that are visible even in modest telescopes from Earth. Each cluster is a small, ancient swarm of hundreds of thousands or millions of old stars, bound together by their own gravity, orbiting Andromeda on long, looping paths. Threaded through Andromeda's halo are several stellar streams, long ribbons of stars left behind by smaller galaxies that Andromeda has absorbed over the course of its history. The most prominent of these is the Andromeda Giant Stellar Stream, which loops around the southern part of the galaxy and contains the remains of a small galaxy that was disrupted by Andromeda in the distant past. The stream is one of the largest known stellar streams in any galaxy, with a length of hundreds of thousands of light-years. There are other smaller streams as well, each one the soft afterimage of a small galaxy that no longer exists as a separate entity. If you continued inward through Andromeda's halo, you would pass through dwarf companion galaxies on long, looping orbits. Andromeda has more than a dozen known dwarf companions, including the 2 relatively bright ones called Messier 32 and Messier 110, which appear close to Andromeda in long-exposure photographs and are visible as small, bright patches near the main disk. Messier 32 is a compact, elliptical galaxy, dense and small, and may be the remnant of a larger galaxy that has been partly absorbed by Andromeda. Messier 110 is a small elliptical with a slightly tidally distorted shape, suggesting it has had close encounters with Andromeda in the past. There are also fainter companions: Andromeda the 1st, 2, Phi, 5, X, Xi, 12, 13, 15, 16, and others, numbered in order of discovery, each one a small, faint, old galaxy with a few thousand to a few million stars. The transition from halo to disk would be gradual. Andromeda's disk is roughly 220,000 light-years across about twice the diameter of the Milky Way's stellar disk. It is a barred spiral, with prominent spiral arms, a bright bulge at the center, and a large central black hole. The disk contains roughly 1 trillion stars, possibly more depending on the estimate. That makes Andromeda the largest galaxy in the local group by stellar count, though the Milky Way is comparable in total mass when dark matter is counted. From the outer edge of the disk, you would see the spiral arms wrapping around the central bulge, with dust lanes threading through them, and bright young blue stars clustering along the arms. The disk's structure is similar to the Milky Way's, but a bit different in detail. Andromeda is slightly more dominated by its bulge, the central region of older stars surrounding the core, while the Milky Way has a more prominent bar and a slightly less prominent bulge. Andromeda also has a famous infrared star-forming ring, a roughly circular band of star formation about 30,000 light-years from the center, where gas is concentrated and new stars are still being born at a steady rate. The ring is visible most clearly in infrared images that pick up the warm dust glowing from the heat of newborn stars. The center of Andromeda is one of the more unusual features of the galaxy. At the very core sits a supermassive black hole, several tens of times more massive than the Milky Way's central black hole. Around it is a dense nuclear star cluster, a small, very crowded region of stars at the heart of the galaxy. And in even closer to the center, astronomers have observed a peculiar double nucleus, what appears to be 2 bright peaks of light, very close together at the core. The double nucleus is now understood to be the result of an eccentric stellar disk orbiting the central black hole, with stars piling up at the far ends of their eccentric orbits, creating two brightness peaks rather than one. It is a rare and beautiful structure, observed in only a small number of galaxies. If you continued inward through the disk, you would pass through Andromeda's spiral arms, one at a time. Each arm is a region of slightly higher density than the surrounding disk, where new stars are being born. The arms are not solid structures, they are density waves, gravitational ripples that move slowly through the disk and cause gas to compress and form new stars as they pass. Each arm contains its share of nebulae, open clusters, and bright young stars. The dust lanes that run along the inner edges of the arms cast soft shadows visible in the galaxy's overall appearance. The arms wind in a slow, graceful spiral around the bulge. Closer to the center, the bulge of older stars takes over from the disk. The bulge is roughly spherical, dense, and dominated by old stars that have been orbiting the galaxy for most of its history. There are no significant star-forming regions in the bulge. The gas needed for new stars has long since been used up or driven outward. The stars there are old, mostly red and orange in color, and they orbit the center on a wide variety of paths, some nearly circular, some highly elliptical, some plunging close to the central black hole and back out again. And at the very center, the supermassive black hole sits in its quiet sovereignty. It is, by any measure, a substantial black hole heavier than the Milky Ways by a factor of tens. But it is currently quiescent, not actively feeding on much gas, and so it is not lighting up the center of Andromeda with a quasar-like glow. It simply rules its small region by gravity. Stars orbit it in a tight inner cluster. Gas occasionally falls into it. Otherwise, it is one of the quieter big black holes in the universe right now. It has had more active periods in the past and may have more active periods in the future, but at present it is in a slow, soft state. The journey from the outer dark matter halo to the disk would, in actual distance, be hundreds of thousands of light years. Even if you were moving at very high speeds, it would take a long time. But unlike the long crossing of the intergalactic medium, this final leg would feel different. The density of stars around you would rise. The atmosphere of the galaxy would thicken. The light reaching you would become brighter as you approached the central regions. You would be inside a galaxy again, after the long crossing. And the galaxy you would be inside would be the same kind of galaxy as the one you left, a large, mature spiral with its own halo, its own atmosphere, its own dark matter, its own family of companions, its own quiet central black hole. The two galaxies are very much siblings. Looking back, the Milky Way would be behind you in the sky, a small, bright spiral seen from outside, growing smaller as you continued forward. Looking ahead, Andromeda would fill more and more of the view, growing larger as you approached. The local group would be all around you. The cosmic microwave background would still bathe everything. The intergalactic medium between the two galaxies would still hum with its slow conversation of light. You would have crossed the great in-between, and the other side would be waiting for you with the same gentle attention the home side gave you when you left. The crossing is not made by anyone, of course. No human probe will reach Andromeda for any meaningful timescale. The journey is imagined, but it is real. In another way, it is the path light takes every 2.5 million years. The path cosmic rays take, the path neutrinos take, the path gravitational waves take, the path dark matter has structured the universe along for 13 billion years. The path is there. The crossing happens. And the galaxy on the far side is waiting in its quiet sovereignty, the same way our galaxy waits on this side the same way every galaxy in the universe waits at its own distance for whatever light reaches it. Distance in the universe is never just distance. It is also time. Every measurement of how far apart things are is also a measurement of how long it takes light to travel between them. The Milky Way and Andromeda are 2.5 million light-years apart. That is a number that means two things at once. It means that, if a spacecraft could travel at the speed of light, it would take 2.5 million years to make the crossing. It also means that the light from Andromeda reaching the Milky Way tonight left Andromeda 2.5 million years ago. The Andromeda you see in the sky tonight is the Andromeda of 2.5 million years ago. You are looking into deep time whenever you look across the gap. 2.5 million years is a long time by human standards, but a short time by cosmic standards. The Earth is 4.5 billion years old. The universe is 13.8 billion years old. The Sun has been shining for roughly 4.5 billion years and will continue to shine for roughly 5 more before it begins its slow expansion into a red giant. Against those numbers, 2.5 million years is a small fraction. The crossing between the Milky Way and Andromeda, in terms of light travel time, is a small piece of the larger histories of either galaxy. The galaxies have been around for far longer than the crossing takes. At speeds, humans can presently produce somewhere around 17 kilometers per second for the fastest probes we have ever launched. The crossing would take roughly 75 billion years. That is many times the current age of the universe. Even at speeds approaching the speed of light, the crossing would take 2.5 million years from an outside observer's perspective. But for the crew of a near-light-speed ship, the experience would be different. Time dilation would shorten the trip from the crew's perspective. At sufficiently high speeds, within 1% or so of light speed, the crossing could be experienced as a few decades by the people on board, even though the universe outside the ship would age by 2.5 million years during the same trip. This is the strange gift of relativity. Distance at high speeds becomes shorter for the traveler than for the rest of the universe. But no one has any way to build such a ship. The energy requirements are enormous. The engineering challenges are extreme. The trip remains, for now, in the realm of imagination, not because the universe forbids it, but because the universe is so vast that the engineering required to cross it at high speeds is far beyond anything humans can currently attempt. The journey to Andromeda, in any practical sense, will not happen in the near future. It may not happen for hundreds of generations, or thousands. And it may, in fact, never happen. This is not a sad thought. It is just an honest one. The universe is large, and the distances are slow. The journey to the next galaxy is the kind of journey that the universe itself makes, slowly, with light and gravity and patience, while we make smaller journeys in our own much smaller lives. The crossing happens, just not by us. The intergalactic medium is being traveled all the time by photons, by neutrinos, by gravitational waves, by hypervelocity stars, by gradually drifting cosmic dust. The crossing is the universe's own ongoing motion, and our part in it is to watch from one side, with quiet attention, while the other side does the same. And the gap is slowly closing. The Milky Way and Andromeda are approaching each other at roughly 110 kilometers per second along their line of sight. The tangential motion between them is smaller, but still being measured precisely. Recent measurements have softened the once certain prediction that the two galaxies will collide head-on into something more like a probable but not guaranteed merger. The two galaxies might still pass close enough to merge into a single elliptical galaxy in roughly 6 to 8 billion years. They might pass close enough to be tidally disturbed without fully merging, in which case they would continue to orbit each other for many more billions of years before eventually settling together. The exact outcome depends on the precise tangential motion, which is still being refined as measurements improve. Either way, the merger, or the close pass, or the eventual settling together would not be a collision in the dramatic sense. Galaxies are mostly empty space, even where their stars are concentrated. When two galaxies meet, almost no individual stars actually collide. The stars pass through each other's regions on long, slow orbits, deflected only gently by the combined gravity of the encounter. What changes is the shape of the galaxies. The spiral arms become disrupted. The disks become distorted. Gas clouds collide and trigger waves of new star formation. Over hundreds of millions of years, the two disks would settle into a single elliptical galaxy, with the combined mass of both spirals and a single supermassive black hole at its center, formed by the slow in-spiral of the two original central black holes, is less than #0. 5# is greater than. The result is sometimes called Milkomeda, a contraction of the names of the two galaxies. But Milkomeda is far in the future. By the time it forms, the Sun will have left the main sequence and become a red giant. The Earth, if it still exists, will have been scorched or possibly engulfed. Any human descendants will have either gone extinct, evolved into something unrecognizable, or, if they are very fortunate, found a way to live elsewhere in the galaxy. The merger of the Milky Way and Andromeda will not be a human event in any meaningful sense. It will happen long after humans, in their current form, are no longer here. So the merger is not really our concern. It is the concern of the universe. And the universe is patient. The two galaxies will continue their slow approach for billions of years before anything dramatic happens. The crossing distance will slowly shrink. The atmospheres of the two galaxies will continue to overlap more and more deeply. The dark matter halos, already touching, will eventually become a single shared halo. The cosmic microwave background will continue to fill the in-between with its faint, ancient glow. The intergalactic medium will continue to drift in its slow filament. The local group will continue to be a small family on a small filament of the cosmic web. The Milky Way and Andromeda will continue to draw closer, the way two old friends might draw closer over many years, until they finally settle into a single shared room. The closing is not a tragedy. It is just the natural slow consequence of gravity. The local group is gravitationally bound, and gravitationally bound systems do not stay apart forever. They draw together over deep time. The Milky Way and Andromeda are doing what every gravitationally bound pair of galaxies does. They are slowly settling into one another, on a timescale far longer than human civilization will last in any recognizable form, on a timescale comparable to the lifetimes of stars, rather than the lifetimes of people. If you imagine the journey in reverse, if you imagine the Milky Way reaching out across the gap toward Andromeda, then you can also imagine Andromeda reaching back. The two galaxies are both moving, both pulling at each other, both slowly closing the distance from their own sides. The crossing is mutual. The arrival is mutual. The eventual settling is mutual. There is no one approaching and another waiting. Both are approaching. Both are waiting. The slow motion is shared. This is one of the more peaceful ways to think about the long crossing. It is not a one-way trip. It is not a journey from a home that is here to a destination that is there. It is a shared slow motion of two great galaxies, both of which are home to many things, both of which are quiet, both of which are coming closer to each other in the patient way of cosmic time. For the listener, for anyone tonight, imagining the crossing from somewhere on Earth, in a small room, with the night around them, there is nothing to do. The crossing does not require any participation from you. The Milky Way and Andromeda will continue their slow drift toward each other, whether anyone watches or not. The intergalactic medium will continue to drift in its slow filament, whether anyone studies it or not. The cosmic microwave background will continue to fill every cubic meter of the universe, whether anyone listens or not. The cosmic web will continue to thread the universe in its quiet way, whether anyone maps it or not. You are not asked to do anything. The universe is doing it. It has been doing it for billions of years. It will continue to do it for billions more. Your role, if any, is just to be aware of it for a brief moment, to know that the soft sea is out there, between two soft galaxies, beneath an ancient glow, threaded through a vast scaffolding, held together by patient gravity. That is enough. You do not need to act on this knowledge. You do not need to interpret it. You do not need to do anything with it. You can simply know it, gently, and let the knowledge rest in the same place where all gentle knowledge rests. The night around you is small. The galaxies are far. The crossing is patient. Andromeda is approaching the Milky Way at 110 kilometers per second, somewhere out there, beyond all the things in your room, beyond all the things in your sky, beyond all the things you have ever or will ever touch. The approach is slow enough that no one alive today will see any of it change. The approach is real enough that, given enough billions of years, the two galaxies will eventually become one. And in the long, soft middle between them, in the intergalactic medium that fills the gap, in the dark matter that bridges the gap, in the cosmic microwave background that bathes the gap, in the cosmic web that scaffolds the gap, in the slow shared motion of all the local group's small members, there is room. There is always room. The universe is not crowded. The universe is patient and spacious, and it has been patient and spacious for a very long time, and it will continue to be patient and spacious for a much longer time still. The space between us and the next galaxy is not empty. It is layered and structured and lit by an ancient glow and threaded with gravity and full of slow conversation. It is the largest reservoir of ordinary matter in the universe. It is the medium through which everything else moves. It is the soft sea in which both galaxies drift. It is the place where the two halves of the local group meet. It is the patient middle of a patient cosmos, and it has always been here. It will always be here. And tonight, somewhere out there beyond all the closer things, it is still here, doing its slow, gentle work, while you let the day fade away and the night settle, and the soft, long quiet of the deep universe hold its place in the sky above you, exactly as it has for 13 billion years, and will for many billions more. And so we let the great crossing rest where it has always rested, in the patient space between two slowly drifting galaxies, lit by an ancient light, threaded with quiet structure, neither empty nor full. There is no need to make the journey tonight. The space between will keep its slow shape, whether we travel through it or not. Let your breathing slow. Let your shoulders soften. Let the long dark settle gently around you. Sleep well, and good night.